Alright, so in this video we're going to cover what the heck do we do when we have a force applied at an angle. So the first thing we're going to review is the idea of components. Now we've already done components with velocity. When we had objects launched at angles, right, we found the x and the y components to tell us how fast this object was moving horizontally because we knew ax was 0, and how fast this object was moving vertically because we knew ay was -10. So having those components was really helpful. Same thing is going to be true with forces. So we're going to quickly run through how do we find those components given some different angles. Okay. So let's say we have a force F at an angle theta. Now this angle would be considered with the horizontal because it's with the kind of the horizontal side of the triangle. That horizontal side of the triangle would be called the x component. Vertical side would be called the y component. Okay. Now we can use SOHCAHTOA to figure out how to find those x and y components. This x side is adjacent to the angle, and y side is opposite to the angle, and of course the force itself would be the hypotenuse. So that force F could be like a force applied at an angle, a tension force at an angle, any sort of force. So since Fx is the adjacent and F is the hypotenuse, okay, that tells me adjacent hypotenuse, that sounds like cosine. So the cosine of that angle would be Fx over F. So if I wanted to find Fx, I can cross multiply. So I get Fx equals F cosine theta. I can do something similar for Fy. So with opposite and hypotenuse, that sounds like sine. So sine of theta. Fy over F. I cross multiply, so my y component here would be F sine theta. So that's how I can find the components with the angle with horizontal. Now this other example that we have, this angle here is considered with vertical. It's with the vertical side of the triangle. Okay. Now that's going to change up how I find Fy and Fx, because now Fy is adjacent to the angle and Fx is opposite. So that means now Fy, I'm going to use cosine to find. So cosine of theta is Fy over F. So now Fy is F cosine theta. And Fx is the opposite, so I'm going to use sine. So sine of theta is opposite over hypotenuse. So the x component is now F sine theta. So depending upon what angle we're given, that's going to help us determine how do we even find those components. Okay. We do that with sine and cosine. So that's the component part. So now let's get into some examples. Okay. Now we've already covered tensions at angles, but I do want to review it. Our first step, of course, is going to be a free body diagram. So acting on this mass M, we have a force of gravity. I have this tension, which is at an angle with horizontal. And I have this second tension, which I'm going to assume is nice and horizontal. So if I was asked to draw a free body diagram for a question, this is what I'd draw. Now I can redraw this with the components of F1, and I'm going to redraw it to help me. So this isn't what's actually acting. Right? This free body diagram is what's actually acting. This is the one that kind of makes my life more convenient because it allows me to see how the y component of the tension and gravity should compare and how the x component of the tension and that other F2 should compare. Now here, this block is at rest. So I have a net force in the x direction equals 0. And the net force in the y direction equals 0. So in the x direction, I have an F1x minus F2 is 0. So F1x is really going to be F1, the angle with horizontal, so cosine theta has to equal F2. And then in the y direction, an F1y minus Fg is 0. So F1 sine theta has to equal mg. Okay? And this equation in the y direction allows me to find F1 by just dividing by the sine of theta. And then once I have F1, I could substitute that in here and solve for F2. So having those components can be really, really helpful because it allows me to solve the problem. Again, this is like our official free body diagram, what we would draw for the question. And then this is like our helpful one, the one that we draw to help us out. Okay. So keep that in mind. We might have two different free body diagrams. So then we're going to talk about when we apply forces at an angle and how when we're on a surface that might change our normal force and our force of friction. Because we're very used to our normal force being exactly equal to the force of gravity. That is not always the case. Okay. So the first case we're going to talk about is where I have some applied force applied at an angle. And I'm going to say that the coefficient is greater than 0. Not always on a friction surface, but let's pretend we are. So my free body diagram here, oops, the page moved on me. I have this force F. I have an Fn, I have an Fg, and a force of friction. And this angle is with the horizontal. Okay? So that's my official free body diagram. My helpful free body diagram look like Fg. Opposite of Fg, we have an Fn, and then we have an Ff. We have an Fy, and remember we want to, when we have two forces pointing upwards, we want to make sure that our arrows are parallel to each other, not overlapping, not doing like weird things like that. Okay. And then I have an Fx. Okay. So this free body diagram is really helpful because it helps me set up my net force equations much easier than this one. So in the y direction, I know that my net force has to be 0. Now I have two upward forces, the normal force and the y component. So both of those forces together support Fg. So what that means is my normal force doesn't have to equal Fg to balance the forces. My normal force is now going to be less than Fg because this additional y component helps support the force of gravity. So the surface doesn't have to push up as hard. So what that means is if the surface is not pushing up as hard, these surfaces are not pushed together as much, right? We've kind of decreased the pressure, if you want us to think about it that way. So we'll talk about why that matters in a second. In the x direction, I'm going to assume that I'm accelerating. So I have my x component minus my force of friction is ma. My x component would be f cosine theta. I could substitute in here f sine theta if I wanted. My force of friction is the coefficient times the normal force. Now again, we're really used to the normal force equaling the force of gravity. So a lot of students will kind of autopilot and write mu mg here. That's not going to be the case because like we just talked about, oh no, this is not erasing. There we go. Okay. Like we just talked about, my normal force is less than the force of gravity. So my normal force does not simply get plugged in as mg. Instead, my normal force is going to get plugged in as fg minus fy. And again, this equation better supports that the normal force is less than the force of gravity. So once I plug in for the y component, this looks like mg minus f sine theta. So this whole thing gets plugged in for the normal force. It gets real ugly real fast. We don't have a lot of pretty equations in physics. This is mg minus f sine theta equals ma. Okay. So what this is showing me here is that this force of friction is less than if I just had like a horizontal applied force. So not only does the normal force decrease in this situation from what it normally is, the force of friction also decreases. So that's why it's kind of helpful to pull up and to the right on an object that you're trying to move, because then you're decreasing that normal force, which decreases the force of friction, making it easier to accelerate. So let's talk about kind of the opposite of this situation. Now, I use this picture because it's probably the best thing that I can draw. It's a lawnmower. It's probably the only thing I can draw that looks accurate. But let's say I'm mowing the lawn. Okay. So acting on the lawnmower, because that's what we're going to draw our free body diagram. That's our system. Acting on the lawnmower, I have a force of gravity. And I don't know if you know this, but there is friction on your lawn. It is not a frictionless surface. We have a normal force, and I'm kind of pushing down and to the right on the lawnmower. So my arrow is going to go down and to the right. Okay. And we're going to use the angle with horizontal again. So there's my official free body diagram. My helpful free body diagram is going to look like FG, FY, FN, FX, and FF. Now here, this probably gives us a better indication of how the heck is that normal force going to compare to the force of gravity. From this alone, you might be able to see that the normal force has to be greater than the force of gravity, because the surface not only has to support the force of gravity, but also that additional downward force from me pushing the lawnmower. So that's going to cause that upward force from the surface to increase. So these surfaces are pressed together more. Think about how that might affect friction. Okay, so in the y direction, not accelerating, so the lawnmowers do not jump off the surface. That would be terrifying because there are blades underneath there. So we have a normal force minus Fg minus Fy equals 0. So my normal force is Fg plus Fy. Again, this supports mathematically that the normal force is greater than the force of gravity. In the x direction, we're again going to assume that we are accelerating. Okay. So I have Fx minus that force of friction is ma. So F cosine theta mu normal force. And again, I'm not going to autopilot and fill in mg for the normal force. Instead, I'm going to remember that my normal force does not equal my force of gravity here, but instead equals the force of gravity plus the y component. Okay. Equals ma. And again, this supports the idea that the force of friction has increased from what we normally see, right? That's because with that addition of the downward force, the normal force increases. And since friction depends on the normal force, if the normal force increases, then friction increases. So what that means is the harder I push down on that lawnmower handle, the harder I'm making my job. So if you're trying to mow the lawn with the least amount of effort, you want to try to push more forward than down and forward. So try to push down on the lawnmower handle as little as possible. You just kind of push the lawnmower forward. That way you're not increasing your normal force too much, increasing friction and then making it harder. But that's forces at angles. So basically, as a review, whenever we have a force at an angle, we're going to find its component. And we're going to find its component because that allows us to do net forces in the x and in the y direction, right? Those components are very helpful because they allow us to combine that applied force with other forces in the x and y direction. And that's going to be it for forces at an angle.